Hi, everyone. I'm excited to be part of this year's Women in Data Science Conference. I wanted to talk to you guys about some work that we've done in collaboration with the Greek government on using data science and machine learning for targeted COVID-19 testing. For me personally, this was one of the most impactful uses of using data science and machine learning for a public health context, which is really why I got into this area. So I'm excited to share some of that with you. And this is joint work with Kimon Drakopoulos and Vishal Gupta from USC, as well as a whole bunch of people from the Greek COVID-19 task force, which included public health experts, epidemiologists, and so on. So the problem here was that Greece, in the beginning of 2020, we just all learned about COVID, and so they'd gone into a lockdown, and they had very, very few cases. But with the summer coming up, they got pretty nervous because tourism is actually a huge chunk of their economic activities, 25% of their GDP. And so they knew that they basically had to open their borders to non-essential travel in order to keep their economy going. But at the same time, if they open up their borders to all travelers, they were also very worried that there would be significant public health consequences because a lot of infected but asymptomatic travelers might come into the country and infect the rest of the population. So what do you do when you're faced out with this trade-off between public health and economic activity? Well, ideally, the best thing to do is to test everybody that's showing up at the Greek border. If they test positive, then you ask them, please, self-isolate and quarantine so you don't infect other people. But if they test negative, then you say, hey, go on vacation, spend as much money as you can while you're here. But unfortunately, this time, we didn't have rapid testing kits. People were relying on PCR testing, and those supply chains were very strained as it was. So it just wasn't possible to test the number of travelers that were showing up on the Greek borders. And so what we did was to do the next best thing, which is to test people who are most likely to test positive. Because those are the people, that way using a limited testing budget, we can catch as many positive cases at the border as we can, so we can slow the infection spread within the general population while we're maintaining good economic activity. So we released a tool called AVA that did this. It was basically a real-time data-driven system that allocated Greece's limited testing resources to recommend who to test. As a consequence of some of these risk estimates that we were maintaining, it also identified hotspots which informed the Greek Prime Minister which countries to gray list. So gray listing is a political action that basically disallows travelers from certain countries from entering Greece without producing a negative PCR pretest from the last 72 hours. So they really hated gray listing any countries because it has strong political and economic consequences. So whenever we gray listed a country, we saw that arrivals dropped steeply from that location. So it's something they really do not want to do. But then if it's necessary for public health, they will do. And finally, we offered interpretable insights to the Greek government for domestic decision making. So if I know which areas are looking risky, we show that to them on a dashboard. They can use that information to decide where to deploy mobile testing teams or have ad hoc social distancing protocols and so on. So this is roughly a schematic of how AVA works. Every day during the pandemic, we would get about 30 to 100,000 passengers who are arriving. This is actually very little for Greece because this was pandemic numbers. So they're arriving either by land, air, or water. 24 hours prior to travel, families fill out something called a passenger locator form. And this basically serves to collect a bunch of features. They tell us where they're coming from, demographic information, and so on. All of this gets fed into our system, which again is called AVA. And like I said, most people can get tested because they have very limited testing resources. So we recommend a subset of 6,000 to 8,000 travelers to get tested based on the features that they've reported and our current risk estimates. And so these guys will get a QR code that gets scanned. And so they step behind one of these curtains. This is from a particular airport. They get their swab taken, that gets linked to their QR code, and then the sample gets shipped out to a lab. And then within 24 to 48 hours, we have contracts with labs at different points of entry. They will return those results back to our database, and so we can use that to update our predictive models and make the next set of testing allocations. So this dynamic feedback loop here is really what makes AVA interesting and effective. because as you can imagine, the pandemic was very non-stationary or dynamically evolving in different parts of the world. Various locations would spike up in risk and then become safe again. And so we really need to be agile in how we respond to these risk estimates. And so by constantly updating our predictive models with new data that we are actively collecting at the border, we're able to stay agile and respond within a short time period to different spikes that were showing up in different places. So this was a pretty large-scale operation. It spanned about 40 different points of entry throughout Greece. There were about 400 medical professionals and 300 border agents in the supply chain. They were contracting with 32 different labs across Greece to make sure that we got the results back in a timely manner. And then ultimately, this all fed into a number of dashboards that we helped design, and we had various policy recommendations through meetings with the COVID-19 AVA Executive Committee. This is a picture of my co-author, Kimon, with the Greek Prime Minister, Kyriakos Mitsotakis, where they were discussing kind of how they should proceed with domestic decisions based on AVA's risk estimates. So if I were to just add a little bit of math here, if we're thinking about our primary objective, it's to catch as many infections we can at the border. So what we want to do is we want to discretize the different types of passengers that we are observing based on their feature information. So a given type K passenger has a test outcome that's like a Bernoulli random variable draw around some expected probability that they will test positive that I'm going to call RK of T. So this depends both on the type that they have as well as the time step, because again, the pandemic is very dynamic or non-stationary. And the decision that we're making really is the number of passengers to test on any given day of any type at any entry. And this is all subject to a number of constraints based on the testing budgets and how many people are actually showing up at that entry. But this is really what we are deciding. I'm going to call that NKE of T. And our goal is to maximize the number of infections we're catching at the border. So we're really summing the number that we are testing of each type times the probability that they will actually test positive, summed over all the entries, all the types, and all the days in the summer. So immediately you can see that if we knew this RK of T, so if we knew how risky each passenger is to test positive, this problem is trivial. We're just going to test the people that are most likely to test positive until we run out of tests, right? But unfortunately, one problem here is that we don't know RK of T, and more importantly, our estimate of RK of T, which I call R hat K of T, depends on the testing allocations that we made in the last time periods, right? Because that's the data that we've collected that will help us learn what the estimate should be tomorrow. So if today I don't test any Spanish people, for example, I will not know how risky Spanish people are in the next time period. And so there's this dynamic feedback that we need to account for. So this is actually what's well known in the literature as the exploration-exploitation trade-off. On one hand, you want to explore, you want to test enough passengers from every type at any given time so that I know whether or not they're risky, right? If we don't test people of a certain type, it basically gives a blind spot to the algorithm, which could be risky in the future. And so this is basically just doing surveillance where we're trying to keep tabs on the evolution of risk for every type of passenger. This also ends up being useful for gray listing decisions because ultimately we want to tell the office of the Prime Minister, hey, this location looks like it's getting untenably risky. Maybe we should, stop allowing travelers from there unless they produce a PCR negative test. But really, our goal in this problem is to maximize the number of infections that we're catching at the border. So this means we want to really aggressively test people who are coming from the riskiest types, even if we know that they're already risky. And that way we quarantine the most positive cases. So this gives us that trade-off. So there is a little bit of a tension between these two things, and a good algorithm will balance the two. And so there's been a lot of work on bandit algorithms that do this. So upper confidence bound, Thompson sampling, Gittins index, and so on. So we basically build on this, what is known as the contextual bandit literature to design our algorithm. There are a couple of challenges that show up that are sort of unique to our setting. So first of all, we have very non-stationary underlying reward functions. So what we do is basically we have a rolling window for our predictive models. We throw away old data. We have batch decision making as well as delayed feedback. So this is an operational constraint because what we really don't want to do is have one of the border agents lose their internet connection, say at a port of entry, not be able to figure out who they should be testing, and then end up having a bunch of people pooling in the airport and infecting each other, right? So what we do instead is we get the passenger manifest the night before, we make all our testing allocations for that day, and we release them. And that way we don't have any of these real-time updates that might suffer from various operational issues. We also have delayed feedback, so it's not like we test someone and we immediately see the feedback. It takes us about 2 days for us to get the results back from the labs. So we kind of need to account for the expected information that we are going to get from the labs. And we have a bunch of budget constraints. So we designed an algorithm that kind of addressed all of these issues. Of course, I don't have time to get into the actual specifics of the algorithm, but I'll show you some results of how it looks within a given day. So what I'm showing you here are actual arrivals and testing allocations within a given batch or a given day that actually happened in the summer of 2020. Because this is real data, I had to anonymize both the X and the Y axis. But what we're seeing in the X axis are different countries or cities that people are coming from. The teal portions of the bar are the people that we are testing, and the entire bar represents the number of arrivals. So you can see, and the countries or cities are ordered from high risk to low risk. So you can see that when in the high risk side, all of the bars are completely teal. So that means that we are testing 100% of these arrivals. So that's exploitation. We're trying to find the most positive cases. But on the low risk side, we see that we are still testing a small number of people in every single type, so that we're doing exploration. We're trying to figure out if these guys are changing and they're becoming riskier over time. But ultimately, we're not testing most of them because we have a limited testing budget. And you'll see that the last bar is actually mostly teal. So that happens because we have various testing constraints. So this is a map of the different points of entry in Greece, and you can see that they're colored in blue or red. So a blue point of entry here means that we have lots of, relatively speaking, we have lots of tests per arrival. If it's a red icon, it means that we have very few tests per arrival. So you can see that there's a lot of heterogeneity depending on where you're actually showing up, because Greece is a bunch of islands. It's not that we can ship out our tests to a lab that is very far away and get the results back within that 2-day time window that we've promised. So we can only ship to certain labs, and those transportation constraints induce some inefficiencies in the supply chain. And more interestingly, the kinds of people who show up to these different points of entry are not uniform, right? So we see that German travelers, that's DE, they show up at any point of entry. So red here means large numbers. But Northern Macedonians, that's MK, first of all, they show up in much fewer numbers, but they only show up to a handful of points of entry where we see these orange boxes. And so that means that we need to save testing budget to actually test Northern Macedonians at these specific points of entry, whereas for Germans, we can kind of test them anywhere. So these are things that we want to account for in the algorithm. So that's the actual allocation procedure. There's also an interesting statistical estimation issue that shows up here. So for every type, ultimately, I have a bunch of testing results. I need to figure out if they're risky or they're not risky. And this is easier, this is harder than it sounds because we have very imbalanced data. So on average, only 1 in 500 people randomly selected will test positive, which is great from a public health perspective, because if a lot of people are testing positive, we don't want to open up for tourism. But it's not great from a statistical inference perspective, because even if I'm testing thousands of people, I'm only getting a handful of positives. And on top of that, these features are pretty high dimensional, like where they're coming from. That origin, city, or country is a categorical feature with tens of thousands of levels. So if we look at any snapshot of our data, we actually see that most countries have less than 200 passengers from the previous 2 weeks. So that means that it's pretty challenging to get good prevalence estimates for these locations, which obviously makes it tricky for the downstream testing algorithm. And you can use kind of black box machine learning algorithms, but they also produce pretty unstable or inaccurate estimates for these data poor countries. So here we did a simple analysis where we took real data. This is the kind of dashboard that we would be showing to the policymakers. So the pink bar here is basically showing the risk estimates from a gradient boosted machine, which is a black box machine learning model that's very successful. And then we slightly perturbed the data by throwing in a single positive type A passenger. And what we saw is that we expect that the type A passenger's risk, so the teal bar here is a perturbed metric, increases, but what you don't expect to see or you don't want to see is that type B passengers, so this is from passengers from a completely different country, had an 81% drop in their prevalence. Type G had a 500% increase in their prevalence. So this is because type B and type G don't have a lot of data, and so they respond erratically to slight changes in the training data, which from a policymaker's perspective is not great, because that means that the underlying model may not be reliable for making these downstream decisions for things like gray listing. So what we did was we built a transfer learning approach that relied on lasso and empirical Bayes to kind of share knowledge across different passenger types or countries, so we could get a pretty good mean squared error out of sample while preserving interpretability and stability. So let me move on to whether this actually worked. So we can use a technique called inverse propensity weighting to understand how our algorithm that we actually deployed performed in response to a counterfactual approach like random testing, which is what Greece was going to do. So random testing is great because it doesn't require any infrastructure. And what we found is that compared to random testing, we get an 85% boost in the number of tests in the number of positive cases that we caught at the border. So in particular, we had about 7,500 tests at the border. If we had used random testing, we would have needed 14,000 to catch the same number of cases that we caught using this bandit approach. And 14,000 tests was about the entire testing budget of the country at that time, so that would include all of the internal testing and contact tracing efforts, so it's a huge supply chain improvement. You can imagine comparing to an approach that does targeting based on public metrics instead. So instead of random testing, we do something a little smarter. So this requires all of the infrastructure that we have built out for Greece, but it doesn't need the bandits or the reinforcement learning part. And we still see that we get a 25 to 45% improvement in the number of cases that we are catching. And this amount is actually free. It's just because we have a better algorithm. So I think this is really what shows the benefit of having these kind of smart, adaptive, data science-based algorithms in terms of actual public health consequences. For various reasons, this estimate is actually a bit of an underestimate, because what is happening under the hood is every time we find a really risky country, we actually ask the Prime Minister to graylist them. So throughout the summer, we graylisted 10 countries based on AVA's estimates that were looking pretty risky, but it's not clear that those countries would have actually been identified if we didn't actually run this algorithm that involved all this exploration. So if we actually try to include that in our improvement, instead of 85%, we actually get over double the improvement compared to random testing. The details are in the paper. One question that we often get in this setting is why we didn't just use public data. So a common metric that the EU was using at this time was the new cases per million that was reported by country. And what we actually see is a little stark. We find that the prevalence that we are seeing at the border does not correlate at all with the new cases per million. So every point here is a country date pair. Ideally, if the public data reflected the population that was coming to Greece to Greece for a vacation, well, then this would be a very nice straight line. It would be a clear positive correlation. But instead, what we are seeing is that the tested population is not representative of the tourist population. This can be due to a number of reasons. It could be socioeconomic status. It could be the fact that people who are traveling to Greece are more risk averse compared to the people who are actually in the general population. They might have lower risk factors. They tend to be younger and so on. We also see lags because of infrastructure issues. So often, because we are doing active testing at the border, we can find spikes in countries 1 to 16 days before the spike actually shows up in the general population. all of this to say that there's a reason that we really needed to do in-house testing. In data science, it's often important that you're collecting the right metric, and that's really what we were going for here. Thank you, and I'll take any questions.
Thank you so much, Hamsa. It was a wonderful talk. I really enjoyed it. I think that we have a couple questions. From the perspective of, other nations, sounds like what you were doing was really on the forefront. So did other countries ask about what you were doing and want to use it as well?
Yeah, we actually got a bunch of interest from other countries in the EU, especially, but we also talked to Canada and I think Belgium and some other places. What they did end up adopting was the passenger locator form itself, where we collect the features. So that was sort of adopted from Greece to the entire EU level. But implementing the algorithm itself involves some expertise, which we weren't able to scale up to other locations, especially in such a short time period.
Okay, so really the limitation was the need to adapt the algorithm to the different country specifics.
Right.
Cool. Another question is, what other factors do we need to consider if we want to apply this in different countries? So I guess this is pushing it. So how would your algorithm change?
Right. So I think it's very specific to, the structure of the data collection, for example. So like a lot of what we were doing specifically had to do with constructing the testing supply chain, making sure every point of entry had a sufficient testing budget compared to the number of arrivals they were getting, that the data would actually get fed back in a uniform time period. You can imagine if some lab is giving you like a 1 week delay and another lab is giving you a 1 day delay, that makes things pretty non-comparable in terms of estimates. And so a lot of the work was really setting up the supply chain on the ground, which I think we'd have to optimize in a way that could enable like effective data sharing across different points of entry to actually be able to run an algorithm like this.
Cool. Let's see. Another question. This is from the audience. I have a ton of my own, but we'll get to them later. The EBA project seems like it would have geopolitical considerations. Did relationships with other nations come into play in regards to gray listing?
Yeah, it did. So that's why the gray listing decisions, this is a great question, were made with human intervention. So they're made by the Office of the Prime Minister. It's not a purely algorithmic decision. We're really providing a sort of decision support tool. Whereas testing at the border is something that's 100% algorithmic. So, whatever the algorithm decides to do, there's no human intervention at that point.
So the Prime Minister was acting as the intermediary.
Right. There are a variety of, exactly, there are a lot of political and economic considerations because the moment you gray list a country, I think it creates some extent of tension or like distrust in their, health system or their COVID management strategy. It also reduces arrivals from that location, which obviously has economic consequences. So it's something that the Office of the Prime Minister kind of dealt with by taking into account various factors.
Oh, this is fascinating. I love it when machine learning actually reads the real world in its setting. It's fabulous. Another question, of the 4 main challenges you listed, non-stationary dynamics, batch decision making, delayed feedback, and constraints, which was the most difficult to solve or work around?
I think statistically speaking, the non-stationarity is the most costly because that means that we're constantly throwing away data. So if we wanted to build, so there's always a bias variance trade-off when you're building machine learning models. So if you want to uncover like really fine-grained, granular, like heterogeneous effects, you can't really do that in a highly non-stationary environment because you have a kind of limited sample size that you're carrying along. The things that we were able to fix are things like, the batching and the delayed feedback. Those are things that, with smarter algorithms, you can do better. But non-stationarity kind of inherently limits you to the small data regime, which, is, if we could remove that would be great, but I don't see that going away from us.
Another question. Can you talk more about why inverse propensity was so helpful? Also, the same question about transfer learning. Is that a type of synthetic data?
Great question. So inverse propensity weighting is just a standard method from econometrics to do counterfactual estimation. So what we're trying to do here is we're trying to figure out, so we know how our policy worked, and we're trying to figure out how other policies would have worked had we implemented a different policy like random testing, right? And if you want to do that, you need to compute a counterfactual, and when you have enough randomness and you don't have confounders like we don't in our system, this is a valid way of getting good counterfactuals. And so this is more of an evaluation technique. It's not part of the algorithm. It's just a way for us to, in hindsight, figure out what the value of the system was, because it was a large financial and engineering investment for Greece. So going forward, they'd like to know, what is the value of kind of investing in this, right, for future public health challenges and so on. The transfer learning was pretty critical as part of the algorithm. So that basically, so like I said, because of the non-stationarity, we have this like small data kind of high variance regime. And so transfer learning is a way of basically sharing data across different passenger types in order to reduce variance. So that was kind of critical to actually making any kind of decisions in this setting, because if not, your variance is too large that you can't do any effective inference.
Well, it's fascinating. So I was actually abroad myself in the fall semester of this year. I was in Israel, which also has a fairly tight control of COVID and testing and all of that. And I think they handled it slightly differently than you were handling it. And the one thing that really struck me is there's a lot of things a smaller country can do. Like Israel is really a pretty small country. Greece is probably also pretty small, although it's spread out over all of those islands.
Right.
How realistic is it to do something like this in the US? Where are the barriers? What are the problems? Could you do anything?
Yeah, that's a great question. So I think a couple things that are kind of critical to making this sort of thing work is that, there has to be agreement across all points of entry. So there would have to be agreement across all states. It would have to be like a federal effort. Even data sharing in the US is quite difficult because this is obviously, sensitive data that has like identifiable personal information. And so that makes things trickier because ultimately you need a centralized database where you're storing all this information, and you need a centralized way of making allocation decisions. So when you have a bunch of decentralized decision makers, like we largely do in the United States, it's a lot more challenging. I think here, like if we had tried to go for something like this, we would have thought about problems more at maybe the state level rather than the country level. Of course, we had kind of unrestricted access between states, but you can imagine doing this for like, general public health testing or something like that, or a university level, right?
Fantastic. Well, I have just been told that we're out of time, although I would love to continue this discussion. It was really lovely meeting you, Hamsa. Thank you so much for your talk. It was really interesting work.
Thank you.
So now we're going to move on into our networking sessions. And this will be hosted by myself and Mary Perk. During this time, you can join us for a live informal conversation. My networking session is going to focus on the skills that you would probably need to learn to succeed in data science, and as well as some of the lessons I've learned from running the data science MSc program at Penn. Mary Perk will be joined by members of the today's industry panel, and she will focus on mentorship in the data science career field. So please feel free to join the networking session via the links which have been provided in chat. Join whichever one you want, or the links I think are also in the email that was provided to you this morning. So I look forward to seeing you all at the sessions. Thank you, everyone.